we're going to focus our coffee break on nonlinear analysis in SimSolid. As we probably already know, there are three types of nonlinear analysis where a linear static would fail to capture what we want to in our simulation. What we're going to focus on today is separating contact, so contact nonlinearity, but we also support material nonlinearity in that we support going past yield, not into actual fracture, but past the yield point, and then geometric nonlinearity where the structural stiffness of our model changes as we load it. So the stiffness needs to update throughout the run. But we'll be focused here on contact nonlinearity. And we will do this with a pretty simple beam model, well, a couple beams bolted together. Open this ParaSolid file. As always here, we see which parts have overlap. Always a good idea to zoom in there. This overlap is on the order of a fraction of a millimeter, and these are full-size bolted beams, so we're going to be able to handle that overlap without any real problems. The next thing that will automatically pop up is the automatic connections. We'll need to know what a reasonable gap and penetration tolerance is for our model. In this case, I'm actually going to choose something that's not ideal. That way we can see how we might manually go in and change a connection if this automated tool doesn't quite get everything. Maybe the scale of one of our gaps is just different in one place than the rest of the model. From here, we can, of course, expand this, look at our connections, show all of them. Once you get past a certain number of connections, I think there are some good checks that don't rely on you to go through every single one of these. The first of these is going to be show disconnected groups of parts. Here it says I have no disconnected groups of parts. We are going to also review the connections. I can see in here the contact resolution. Sometimes we may need to increase the contact resolution. We typically recommend at least two kind of rows of these connection points for each connection. And we can also see how these were made. So what the allowable gap and penetration tolerance was, which parts are being connected, as well as if they are bonded or sliding. But what I'm actually going to focus our attention on right now is the number of points in the contact. And I always like to sort this from smallest to biggest so that I can see where are my areas that maybe only have 1 or 2 points, or maybe disproportionately small number of points compared to other things in the model. So going from 12 to 72 certainly stands out to me. So I'll highlight this and have this, have SimSolid zoom in. And it'd be helpful if we could actually see what's happening. Right here, I see that I am bonding these two parts together, but I only have a dozen points here to do that. That's certainly not enough to actually represent that connection. So we're going to go in here and manually edit this. So at any point, I can manually set up or manually edit any contact conditions that have been made. So let's go ahead and review this. When I hover over each of these, it will highlight which contacts are being selected. So here is that 6 or 12.1. I'm going to edit this. Just for this specific contact, I'm going to change that gap tolerance. I guess I could have left penetration the same, but I'll say fine connection. Now I have a much fuller contact being formed here. I'll say okay. It'll ask if I want to replace the regular connections that this is overlapping with. So I'll say yes. Close. And this is just one reason we encourage you to bring in everything as separate parts rather than starting to merge things, because you'll be able to easily select these different parts and be able to query or edit some of their contact conditions as well as other things about them. We've got all of our connections showed up. Let's go do that check again. And we see the number of points here, the minimum number's gone up to 72, and those 72.1s are bolted connections. We'll need to assign material to everything. In this case, we are just going to apply this generic default steel that comes in. So apply to all of the parts. You now see they have steel labeled beside them. And first we're going to set up just a regular linear analysis. Always good to do the easiest setup first. We like to say crawl, walk, run. So start easy and start adding complexity so you can troubleshoot and make your life a little bit easier if something goes wrong. I'm just going to constrain these ends. Hit OK, and then we're going to add a force. And we'll add this. And we'll put 1,000 newtons downward in the Z direction. From here, we should be able to go ahead and run. As we talked about last time, and perhaps this is a good review even for people who weren't able to make it, but you'll actually see it going through these different adaptive passes. Just for the sake of runtime, I've left this as adapt for stiffness. If you're interested in detailed results though, you'd come up here and go to adapt for stress. Our focus is largely going to be on just seeing the difference and seeing the context separate once we go to nonlinear. Let's go here, take a quick look at our results, make sure they make sense. So what we expect to happen, a downward force here, and these beams constrain overall downward motion. We're going to put a little checkbox for sanity check. I also like to come here and say show true deformation just to make sure nothing is being scaled and distorting what I think is happening. And we've got relatively small displacement on the order of about 1 millimeter. If we wanted to build on this and go to a structural nonlinear, we could of course come here and specify structural nonlinear, but we already have the loads and boundary conditions that we want. So we can come here and simply either update things, just run this one, but let's say we want to compare results. So let's copy the existing structural run. And now I want to specify that these contacts here can be allowed to separate. I suspect there may be some pulling away of these members. In order to make this the active model, you want to have it bolded here. In HyperWorks, this would be like making something current so that whatever I do to the model happens to this structural run. Before I forget, we're still in adapt for stiffness, and then we're going to go in here and specify that we want separating contact. You can combine some of these for certain nonlinear runs, but you'll notice if you try and go check all of them, that you'll see geometric nonlinear analysis with separating contact is not supported. So that's the only limitation. We can't combine geometric nonlinearity with separating contact. For now, we're only going to have separating contact. And so now we need to go in and actually edit these contact conditions. For this beam, let's go in here and you'll have the option to review the part connections. That's going to be those individual dots that define the connection itself. The part contact conditions are going to be the slided bonding separating options. So we'll scroll down here. What we actually want is the contact surface between these two beams. That's going to be connections 88 and 89. We can edit them to make them separating. You'll notice they changed their color coded. Now they're green instead of red. And we'll do the same thing over here. Review the part contact conditions. Change these to separating. And hit close. Now we have these updated custom contact conditions that are specific to this structural setup 2. Maybe we will rename this and call it nonlinear. Just a little easier to keep track once you get a lot of different runs here. We're going to start the analysis and run our nonlinear run. let's go check out the result. If we are just in the linear results, you'll notice this contact response here. There's not really a need to have contact response because the contact is always doing the same thing. It's always bonded or very small sliding, as opposed to being able to separate. Now when we come in here, we get this new option, not only to get contact force, but contact response. I can look at, for instance, the normal force being transmitted through these contacts. And perhaps also interesting here is being able to look at this contact and say, okay, even though I've allowed these contacts over here to separate, if that is what the physics says it will do, they are still closed. They have an opening of 0 millimeters. But over here, these beams are actually starting to separate because of this downward load and actually starting to be pulled apart a little bit. So perhaps I need to tighten these bolts here or otherwise change my results. Or maybe it's fine that they're separating depending on the application. For instance, if we did want to go in here and do some nut tightening on here, because these bolts have nuts on the other end, you'll have to go through nut tightening. If they were blind, you could do the other option, which is bolt tightening. We'll see, we're going to go 2 turns here. Rerun this analysis. I actually haven't done this yet. Go here, see if that change that I made helps at all. So now I'll go here to contact response. Check my opening. And now I see here that these are closed, but perhaps I should have also tightened these bolts because now instead of the separation happening at this connection, it's now happening back here, which maybe is what we would have expected to happen, given that I did this kind of on the fly. But that is today's session, tips and tricks. So we learned how to manually adjust contacts that had been formed. We learned how to apply bolt and nut tightening and how to apply contact nonlinearity.